So this potential flows, if you see, this is one, like for example the vortex flows, or basically some uniform flows, or basically some flow past some cylinder. All these things can be covered under this particular thing, which is potential flows. Okay, so this potential flows this potential flows will actually help you so much in identifying. So this is the first lecture on this concept of potential flow actually. Okay, so this potential flows, correct, right? Okay, this. So potential flows is one very important module actually for 𝐂𝐸 engineering sciences paper, and normally this syllabus is not in mechanical paper alone. Okay, but since when two choice combination is given, always writing mechanical plus 𝐂𝐸 is always beneficial for you. So I've thought of teaching complete 𝐂𝐸 syllabus also in this course. That's why it's a very big comprehensive course. Almost some 116 hours of fluid mechanics sound is being taught here. So we have made each and every attempt to cover every part of the syllabus that's mentioned in both mechanical and also in 𝐂𝐸. If you open the syllabus official document, and we can quickly see that. Before that, I'll show you the official syllabus also, GATE 2023 mechanical, because I'll just spend 1-2 minutes on this so that you can have some better idea. So GATE 2023 website, I think it is a bit slow today. So papers and syllabus, if you click, so anyhow it will get loaded meanwhile. So let us meanwhile focus here. So this potential flows, if you see, this is one general, means like whatever the analysis of flows you have done, like for example the vortex flows, or basically some uniform flows, or basically some flow past some cylinders. All these things can be covered under this particular thing, which is potential flows. Okay, so this potential flows is like a complete division of fluid mechanics, and at the same time this potential flows is means normally if you go for CFD analysis actually, okay, in your advanced studies like MTech or beyond that, if you go for this analysis of, like for example, if you go for this CFD analysis, this potential flows will actually help you so much in identifying velocity potential functions and actually the stream functions. There, when I'm talking about the differential analysis of control volume, differential analysis of fluid systems, when I've talked about potential functions and stream functions, I told you if potential function is given, if velocity potential function is given, calculation of stream function is very easy when in potential flows. This is what I told you, correct? So here what we do, whenever some velocity potential function is given actually for any flow, then we can easily calculate the stream function actually. Okay, we'll see how we can actually do that in this case. Okay, so this is the first lecture of this module, and in this lecture I'm going to introduce you to the potential flows. So what are potential flows, how any flow can be written in terms of some complex potential function, that I'm going to introduce here. We'll talk about the complex potential function, and also we will give some introduction to basic flows, means how to identify this complex potential for any function in general. That's what we will see. Okay, so these are the three things that we are going to look majoritarily in this particular lecture. Okay, now introduction to potential flows. So before introduction, let us have a quick revision of what we have learned already. So we talked about in the last lecture, we talked about the dimensional analysis of some numbers. Actually, this Reynolds number is basically the ratio of inertia to the viscous forces. The Froude number is ratio of inertia forces to the gravitational forces, and this Euler number is ratio of inertia forces to the pressure forces, and Weber number is ratio of inertia forces to the surface tension forces, and Mach number is the ratio of inertia forces to the elastic forces. Okay, so this is F elastic. These things are there here, and if you see, we have written some expressions here. So this is rho v L by mu, and here this is v by root GL, of course a square root of this v by square root of GL. Similarly here the pressure gives you v by square root of P by rho we have done, and Weber number is also square root of this quantity, which is v by square root of sigma by rho L is what we have, and this is again square root of this, which is velocity by acoustic velocity. So these are the important dimensionless numbers that we have seen in the previous lecture, and we talked about them. Correct? Now introduction to this potential flows. So what is basically a potential flow? Generally what we call a flow to be, when we call a flow to be potential flows. Okay, so if you see this potential flows are basically incompressible irrotational inviscid flows, and that's the reason normally there is no viscosity of the fluid that's involved in this flow, so it's basically inviscid flow, and also the flow is irrotational. So that's the reason why in some books or in some places you find this name of potential flows as ideal flows. Okay, when you say a flow is to be ideal, when there is no rotationality of the flow and also there is no viscous effects of the flow. Okay, so that's why this flow is general. Sometimes it's also called ideal flow. In some places you see this as ideal flow, the reason being no viscosity and no irrotationality. Now whenever this is incompressible flow, then definitely divergence of velocity vector means at any point, if velocity vector is given by ui plus vj plus wk, for example w times k bar, then incompressible means definitely divergence of v velocity vector is equal to 0. Then irrotational flows means curl of v is equal to 0, actually half of curl bar, but anyhow you can write curl of v is also 0. And inviscid means there is no viscous effects, mu is 0 actually. Okay, so mu is also 0, dynamic viscosity is also 0. So this is then incompressible, irrotational and inviscid flows basically here. Now if you see, when the function is irrotational or when the flow is irrotational, definitely I told you mathematically if curl of any vector point function is 0, then definitely there is always some scalar point function such that f bar is equal to gradient of phi. Correct? I have told you this statement. I have told you if f bar is irrotational, if f bar is irrotational, there exists a scalar function phi of xyz such that f bar is actually equal to gradient of phi. Okay, so the change of phi is actually given by this vector point function. Correct? So we have seen this. Therefore whenever this curl of velocity vector is 0, there always exists some potential function which is we call velocity potential function, which we have seen these definitions. Okay, I'm just giving you a quick review of what we discussed in differential analysis of fluid systems. Okay, so now if you see, therefore if flow is irrotational, if flow is irrotational, then if flow is irrotational, there exists a function phi which is called velocity potential function. Correct? We have seen this, which is called velocity potential function. Okay, now this is velocity potential function. Then in that case we can know that this velocity vector, therefore this velocity vector is given by gradient of phi. Correct? So gradient of phi, if you see, that's how we'll get the velocity, and that's how we have the components. U is equal to u is equal to dou u by dou x, v is equal to u is equal to dou phi by dou x, and v is equal to dou phi by dou y. Correct? So we have seen, for example, for a 2D flow, we have seen u is equal to dou phi by dou x and v is equal to dou phi by dou y. Correct? We have seen this. Now basically there exists any stream function. So whenever there is some flow, definitely there are streamlines in the flow and there exists some stream function. So therefore for a given stream function for the flow, for a given stream function for the flow, psi of x comma y, so for a given stream function for the flow psi of x comma y, we have also seen that u is equal to dou psi by dou y and v is equal to minus dou psi by dou x, correct? So basically we have seen that this u and v, they satisfy the 𝐂𝐤𝐴 equations, correct? We have seen that. So both u and v satisfy the Cauchy-Riemann equations, CR equations, what you see. Okay, so CR basically Cauchy-Riemann equations, okay, so means basically if you see, we can see dou u by dou x is equal to dou v by dou y, dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. Okay, so this is what we have. Dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. We have seen these things in differential analysis of fluid systems. Okay, and also in polar form, I told you that I'll teach you in mathematics normally how these equations come, but in polar form normally if you see, we have, if v bar is given by radial vector, means radial component and azimuthal component for example, then we have in polar form dou u by dou r is equal to 1 by r times of dou v by dou theta, or generally if you write it in terms of vr and v theta, dou vr by dou r is equal to 1 by r times of dou v theta by dou theta, and dou vr by dou theta is equal to minus r times of dou v theta by dou r, correct? So these are the Cauchy-Riemann equations in polar form. So these are the equations which I have given you in differential analysis. Okay, and also we have seen one thing, the curves phi of x comma y is equal to constant and psi of x comma y is equal to some other constant intersect each other orthogonally, intersect each other orthogonally, okay, so they intersect each other orthogonally. So means basically we have seen the concept of flow net. If these are the equipotential lines for example which are parallel, for example like this, so if these are the equipotential lines, phi is equal to c1, c2, okay, c3, c4 and c5 for example, and then in such case we have this streamlines, which gives you psi is equal to c1, psi is equal to c2, psi is equal to c3, c4, c5 and c6, correct? You have this components. Okay, so we know that at this point of intersection, so this concept is called the flow net, which actually exists here. So flow net, and normally if you want to analyze this, we will analyze in small grids like this. Okay, so this is called a grid. Normally in CFD analysis and all, you see a lot of rectangles kind of thing, lot of meshes and all. They are actually nothing but this flow net. So normally we will split this complete body, or wherever, let us suppose if some part of flow is in your interest, then you will split that particular flow into some large number of rectangles depending upon the grid size. Like for example very fine size, sometimes in micrometers, then we will actually split this element into some large number of elements and we do the CFD analysis basically. Okay, so anyhow, right now this is the concept of flow net, and all these angles are 90 degrees. Okay, so they are intersecting perpendicularly. Okay, so we seen that they actually cut each other perpendicularly, they are orthogonal to each other. So means basically if you calculate d phi or dy by dx of the lines, phi is equal to constant, and the product of the slopes dy by dx of the lines psi is equal to constant is equal to, means let us suppose if you plot this on a xy plane for example, then what is the value? So please type in the chat box. We have seen these things. I'm just giving some warm up for the things of this complex potential function. So please type in the chat box what is this value. dy by dx of constant phi lines multiplied with dy by dx of constant psi lines actually. Okay, so what is the value? -1, correct? Because these lines are actually perpendicular to each other, so this value is -1. So then we also know that both phi and psi satisfy the Laplace equation also. So both phi and psi satisfy Laplace equation. Both phi and psi satisfies the Laplace equation. So basically del square phi is equal to 0 and del square phi is also equal to del square psi is also equal to 0. What's the meaning of these two? This term is dou square phi by dou x square plus dou square phi by dou y square is equal to 0, and coming to here dou square psi by dou x square plus dou square psi by dou y square. So this is also 0 here. Okay, so these are the both equations. So this is the basic background that we have discussed, correct? So are you all clear so far? These are the few points that we have talked about: the velocity potential function and the stream function in case of differential analysis of fluid systems, correct? Now let us try to understand some basics of complex numbers, because this is very much important for you to know how we actually do the things in the later stage. Okay, so basics of complex numbers is very important for you. Okay, like for example, do you all know how to calculate logarithm? Like for example, let z is equal to x plus iy is a complex number, for example. Then let us suppose if z is equal to x plus iy is complex number, then let us suppose you have log z to the base e. Do you know how to calculate this value? Means let us suppose if I give you some complex number 2 plus 3i, 3 plus 4i, something like that. How many? Okay, tell me honestly, how many of you don't know this? It's okay, I'll tell you. How many of you don't know how to calculate this logarithm of complex numbers? Because this logarithm I'm going to use in vertex flows in next lecture, maybe basic flows, when I'm talking about vertex flows, source, sink, these concepts, I'll go for that. Do you all know that if there is some complex number x plus iy, this complex number can be written as r into e power I theta, where r is called modulus and theta is called amplitude? Means how to find the values of r and theta if there is some complex number, for example. Do you know how to calculate these values? Yes, because I have taught you this during differential analysis. You remember when I'm talking about the acceleration components, I have shown you these things. ar is equal to r double dot plus minus r double dot minus r theta dot square, and a theta is equal to r theta double dot plus 2 times of r dot theta dot. So these are the expressions I have derived. At that point I showed you what I've shown you basically what are complex numbers and what does this I actually represent, and how the complex numbers, this two components, are actually coming. Do you remember this? During differential analysis of fluid systems, when I'm talking about the acceleration case, I have gone through these things. If you open your notebook, you might find it actually. I have at this point when I'm doing this analysis, I've told you what is actually some complex number is, what does this I actually tells you. So if you multiply I to any number, that rotates the line by 90 degrees. I think I have talked to you these points, correct? So now if you see this, so any complex number can be written in this form. And look, let for example, okay, let me start at some point. So see here, guys, look here. Let z is equal to x plus iy is written in the form r into e power I theta. Then this implies r is nothing but square root of this x square plus y square, and theta is tan inverse of y by x. Okay, so this is how we get the values of r and theta I have given you at that time, basically from the triangle. Now this e power I theta can be written as, I told you this also, this e power I theta can be written as cos theta plus I times of sin theta, correct? So cos theta plus I times of sin theta, and if you put e power minus I theta, then cos theta minus I sin theta. Okay, let us write that also. We'll use that. E power minus I theta can be written as, this is nothing but putting minus theta in place of theta. So if you put minus theta, this becomes minus I theta. If you put minus theta, cos of minus theta is cos theta. plus I times of sine of minus theta is minus sine theta. So minus I sine theta is what you get here. Okay, so this is minus I sine theta. Okay, so cos theta minus I sine theta. Now, if you see, this complex numbers is written in this form, correct? If you see, Z1 is equal to R1 e power I theta 1, Z2 is equal to R2 e power I theta 2. So if you see, the modulus of the complex number is R1 and R2, because if you see, magnitude of e power I theta is always 1, correct? Whatever might be the value of theta, the modulus of this complex number is always 1, means square root of cos square theta plus sin square theta is 1 for any value of theta, because that's an identity. Okay, now this implies if you do Z1 into Z2, you will get Z1 Z2, I mean sorry, this R1 R2 into e power I times of theta 1 plus theta 2, correct? Similarly, this Z1 by Z2 is equal to R1 by R2 into e power I times of theta 1 minus theta 2. So these are the things that you generally get, because e power I theta 1 into e power I theta 2 gives you a power m into a power n form. So a power m plus n. So I theta 1 plus I theta 2. So if you take I common, theta 1 plus theta 2. Similarly here, m by n gives you m minus n. So theta 1 minus theta 2. Now, if you see, for example, this one property we'll use here in very much in this source and sink combinations is Z1 by Z2. If we have this complex, for example, if you have two complex numbers, then the modulus of this division is equal to mod Z1 divided by mod Z2. Okay, so division is actually equal to individual modulus. Okay, so that's what we have, individual modulus. Now similarly, calculation of this log, because log we are using, will use many times in this vertex flows and all. So let, for example, if you have this complex number z is equal to x plus iy, then log z to the base e is equal to half times of log x square plus y square to the base e plus I times of tan inverse y by x. So this is a complex number, because you see, this is some real number, yes or no? This part which is here for the complex number, so this is called the real part, which we seen in differential analysis. This is a real part and this is imaginary part, correct? So this is imaginary part. Okay, now how do I know that this is the equation? Because this equation is very helpful in writing vertex flows. Okay, we'll see how this equation is very helpful in the next maybe in tomorrow's first lecture we'll talk about it. But right now this equation is very important and very powerful tool to solve vertex flows and also this source and sink concepts. Okay, we'll see how. So first of all, how did I write this expression for log z? Okay, so see that z is equal to x plus iy. So this can be written as r into e power I theta, where theta is this and r value is this given, right? So if you apply log on both sides, log z to the base e is equal to log r into e power I theta to the base e. This can be written as a into b. So log a plus log b can be written log r to the base e plus log times of e power I theta to the base e. Now please tell me one thing. Let us suppose you have this result log x power n to the base a. This is actually equal to n times of log x to the base a, correct? Yes or no? Have you seen this result? So log x power n, if it's there to the base a, this is equal to n times of log x to the base a, correct? Have you seen this anywhere? Normally property of logarithm. So if you keep adding this logarithm n times multiply, that's actually equal to log of this x power n to the base a. Okay, so therefore if you see, this can be written as I theta log e to the base e. So this is equal to log r to the base e plus I theta into log e to the base e. What is value of log e to the same base? So please tell me, log e to the same base e is how much? What's the value? 1, correct? So this is 1. So this remains as 1 here. So this is equal to small r can be written as x square plus y square whole power 1 by 2. This is square root can be written x square plus y square whole power 1 by 2. So using that property, half can be multiplied, before logarithm, half times of log x square plus y square to the base e plus I times of theta value. So theta is tan inverse y by x. Clear? So that's how we get this expression. Okay, so some simple 2-3 steps that gives you this logarithmic expression. Okay, so we will see how to write the complex potential function now and how to actually calculate the velocities from that. Clear? Now let us try to understand. So this is some mathematical background that could be helpful to you in this potential flows or using complex numbers. Okay, so you know how to multiply two complex numbers and all normally. Means let us suppose if we have a plus ib into c plus id, for example, then how do you multiply these two complex numbers? A into c plus id plus ib times of c plus id. So this gives you ac plus I times of AD plus I times of BC plus I into I minus 1, so minus BD. Okay, so AC minus BD plus I times of AD plus BC. So this is how you have the product of two complex numbers. Okay, I'm just giving you some basic idea because sometimes you need some things to multiply some complex numbers. So that's why I'm giving you this background which is required for writing the mathematical analysis using complex numbers. Clear? Okay, now if this is clear, let us work on something else. Okay, so now let us see into the complex potential function. So before complex potential function, I want to give you just one quantity, actually conversion of velocities in Cartesian coordinates to polar coordinates. Velocities in Cartesian coordinates to polar coordinates. Okay, so this is one very important conversion actually, because normally sometimes you don't find this in books, directly they'll give you the results, you may not understand how they have written these equations. So normally if you see, if u v are the components of velocity in Cartesian system, they are given by u r u theta times cos theta sin theta minus sin theta and cos theta. Okay, so this is how you have the things. So basically if you see, this is of size 1 by 2, this is of size 1 by 2, and this is of size 2 by 2. So if you multiply these two, you will again get one expressions. Okay, so if you simplify these expressions, normally what you get is u v is equal to, so first one, u r cos theta minus u theta sin theta. So u r cos theta minus u theta sin theta, and second element is u r sin theta plus u theta cos theta. So this is the expansion, this is the term. So whenever you have a u and v basically here, then this u and v is given by u is equal to u r cos theta minus u theta sin theta, just matrix multiplication, that's it. Okay, and v is equal to the second element u r sin theta plus u theta cos theta. Okay, so this gives you u theta cos theta. Now try to see, so this is the relation that you generally find, but how do you get this relation? It's from simple trigonometry and geometrical applications. So see, I'll give you some hint. Let, for example, if you take this, for example, let us write, let v bar is equal to ui plus vj. Okay, then let us see how do we write this. So let us take the xy coordinate system to understand. So let us suppose this is x axis. Okay, so this is x axis and this is y axis, for example, in this case. So this is y axis, origin x and y, for example, in the xy plane. Now let us suppose you have some velocity vector v, for example. Okay, so let us suppose this is your velocity vector v. So this is your velocity vector which is given by v bar. Now if you resolve this into x and y components, then obviously you know this component which is here is the y component of velocity. So this component is y component of velocity, and this component is x component of velocity, correct, known to you directly. So here if you see, this is u and this is v, correct, it is known to you. So if there is some velocity vector, if you resolve into x and y coordinates, then this is the x so see, this is the x component of velocity and this is the y component of velocity. Now if you convert this to polar coordinates, means let us suppose the same velocity vector, if you resolve into some different thing like this, for example, if you see, let us suppose this is the radial direction and for example this is the theta direction. Okay, so it means basically if you see the same velocity vector, this is velocity in the radial direction and this is velocity in the theta direction, for example radial and theta, and let us say at this instant this is making an angle theta with horizontal. Then you, if you convert this, fine, anyhow let us leave this, no issue. So we have split this v in terms of ur and u theta, so it says that this angle is again 90 degrees. Radial and theta directions are normal to each other. Similarly x and y directions are also normal to each other. You might have seen this case of Merchant circle in two life equations. Okay, so whenever you see Merchant circle, the hypotenuse is actually same, means basically this resultant of the forces is same, but it is resolved into different things, correct. Similarly here the resultant of radial and theta is again this v, and the resultant of this u and this v is again this magnitude of v. Clear? So did you get this? I have resolved this v into two coordinate systems. Basically one is in the Cartesian coordinate system u v, second in the polar coordinate system u r and u theta, such that it makes an angle theta with this base actually. Clear? So is this clear to all of you? First of all, if this is clear, then I will show you how these things are coming, because I'm going to use these things in complex potential functions that I'm going to write in the next stage. If you can understand some first 35 to 40 minutes of basics, then things will be very easy. Clear? Okay, now fine. Okay, now let us see what is the expression for u r actually. Okay, so or u. So if you take this projection, for example, if you take this projection, then let us suppose if you name this for example a and b, for example, then we can write one thing, u is equal to OA. This OA can be written as OB minus AB, correct. This can be written as OB is the total length minus this small length AB. Fine. Now what is this total length OB? Look, this total dimension is UR and this is theta. So can I write OB as UR cos theta? Yes or no? Can I write this? Correct. So therefore this OB can be written as UR cos theta. Then what about AB here? Look, AB distance, if you see this is something like this. So see here, you have this component like this, then you have this line which is lying like this. Okay, so basically this is equal to, if base is here, and this is u theta. So this is u theta component which we have written u theta. So this is u theta. Okay, and we want this distance. Okay, so we want this distance a b. So we want this gap AB. Okay, so if you want this gap AB, look, in this particular triangle we also have a normal like this perpendicular to this. There is some perpendicularly radial direction which is going from here. So if you see, this is the radial direction. Okay, so this angle is 90. This angle is 90. Okay, so now if you see one thing, Look, try to construct this projection here. Okay, so if you construct this projection, for example, like this, so this is C and this is D. So AB is same as CD. AB is same as CD. Now, what about CD here? Look, try to understand carefully. First of all, if you take this angle with horizontal, this angle will be theta. Yes or no? Because you see, the inclination made by this line with this angle horizontal is theta. So obviously this angle is theta. Now, if this angle is theta and this angle is 90, so this value DC is actually equal to this angle. If you can identify, let us see what is that angle. See carefully here. This total angle is 90. If this is theta, this small angle is also theta, correct? Means basically, try to observe carefully. If this angle is theta, then this angle between this dotted line and this horizontal line is also theta. So this angle is 90 minus theta. 90 minus theta. That's it. Okay. So this angle is 90 minus theta. So therefore, if that angle is 90 minus theta, then CD or DC, basically CD can be written as U theta cos 90 minus theta. So this can be written as U theta sin theta actually here. Okay. So this is U theta sin theta. So therefore, this OB is UR cos theta, AB is U theta sin theta. So therefore, your U x component of velocity is equal to OB UR cos theta minus AB, which is the CD, which is U theta sin theta, and this is the same expression that we have written initially using that matrices. Okay, so UR cos theta minus U theta sin theta. Clear? So is this clear to all of you about this conversion of U in terms of UR and U theta? Is this clear to you? Did you understand this? Only thing is just little application of this alternate angles and all. Okay, now let us see, continue for the case of V. V can be written as, so if you can split this to two parts, basically this B, okay, so this component, let us say for example D, okay, D we have already taken, E, let us suppose this is E, and let us, if you mark for example something like this, and let us suppose if this is F, okay, this point is F and this point is for example say something about G for example. Okay, now y component of velocity, this V is equal to AF plus FG, correct? So V is equal to y component of velocity, V is equal to y component of velocity, V is equal to, look, AF plus FG, AF plus FG, correct? Now what about AF? AF is equal to, so AF is this quantity, this AF is same as BE, correct? So AF is same as BE, and what about BE in this case? So BE in this case is nothing but this is UR and this is theta, so this quantity is UR times sin theta. Okay, so we have UR times sin theta. Next, FG. Now what about FG? Again, so for example this angle is 90 minus theta, we have just observed, so this angle is 90 minus theta, correct? Basically from this understanding, this angle which is bounded in the triangle is 90 minus theta. Now if this is U theta, then this component is U theta sin component. Okay, so U theta sin 90 minus theta, which is U theta cos theta, correct? So this is what you have. So when you sum up these things, then velocity, y component of velocity is equal to UR sin theta plus U theta cos theta. Okay, so we have U theta cos theta. Clear? So this is what you have. V is equal to UR sin theta plus U theta cos theta. So that's how these two expressions are obtained by simple trigonometric equations. But you have to use little understanding. They are very simple, but understanding this theta, all these things, lies a little effort. So that's how these two equations are actually the equations in our case. Now why I have taken so much effort in writing these equations, you will come to know once I define the complex potential function. Okay, so I hope this is clear. Conversion of Cartesian components to the what do you say, polar components. Now let us give this introduction to the complex potential function. So first of all, have you ever heard this word called analytic function? Analytic function. So please type in the chat box, what is this analytic function? Have you ever heard about this analytic function? So now if you see this analytic function, normally if you take complex functions, for example, okay, I'll tell you. So what happens, like you have the functions, normally the real functions like x square, x cube, sin x, tan x, whatever. You also have the complex functions, e power z, log z, sin z, z cube, z square, all these complex functions. Now for example, I'll ask you one thing. F of z is equal to, for example, say z cube. I have taken one more function. F of z is equal to log z to the base e, for example. Now see carefully. So this gives you f dash of z is equal to 3z square, and f dash of z in this case is 1 by z. Correct? So this is 1 by z. F dash of z is equal to 1 by z. So this is 3z square, and here this is 1 by z. Now try to understand this. Whatever I keep in place of z, this value always exists. Yes or no? I mean, it will be some number depending upon the value of z what I keep. This will be some value, but this 3z square always exists. Yes or no? Correct? Means if I keep z is equal to some complex number 2 plus i, 1 plus 3i, whatever I keep, then definitely I will get some complex number as an outcome. Yes or no? If I put z equal to 0, then f dash of z is 0 at that case. But 0 is also some value. Okay, it's not some indeterminate form. But let us suppose if I put z is equal to 0 here. In that case, will this derivative exist? Please tell me. Division with 0, is it defined? Division with 0, is it defined actually? Division with 0, is it defined? Not defined. Correct? So that's how some functions, they will actually be differentiable at all points. Some functions will not be differentiable at some points actually. Okay, so basically if you see, this analytic function is that function where if you take for example the plane, which is imaginary part of z, and this is a real part of z. Okay, so this is a real part of z. This is analytic function, of course, and z is as usual x plus iy. Now see carefully here. So when you call a function to be analytic function at a point, for example, is if you take a point z0, for example, x0 plus iy0. So you have taken some point. Whenever the function is differentiable at this point, the function has to be differentiable at this point, and also it should be differentiable at every point within some neighborhood actually. Okay, means the function should actually be differentiable at every point within this neighborhood. Then the function is called this analytic function. Okay, so analytic function. So if you see, the function is said to be analytic at z is equal to z0. The function f of z is said to be analytic at z is equal to z0 if at z is equal to z0 if f of z is differentiable at z is equal to z0 and also at every point and also at every point in the neighborhood of z is equal to z0. Okay, so this is also differentiable at every point in the neighborhood of z is equal. Neighborhood means some points which are close to this. Now, why we are much interested about the differentiability of this f of z, you will come to know very soon. Okay, so see here. Now, how we define this complex function is complex potential function. A complex potential function, for any flow is given by an analytic function f of z, where, or let us write capital F of z. Normally this is the nomenclature that's followed. Capital F of z, where capital F of z is equal to potential function plus I times of stream function, actually plus I times of stream function, actually. Okay, so this phi of x comma y here is called, this is your velocity potential function. Velocity potential function, and this is your stream function. Okay, so this is your stream function. So you have the velocity potential function and also some stream function actually here. Okay, now so velocity potential and also this stream functions. Now, why I want my function to be analytic? I have written this word analytic and I have talked something about analytic. The reason is, look, let us suppose if I differentiate this with respect to x, for example, partially, we have f of z is equal to phi of x comma y plus I times of psi of x comma y, u plus iv form basically. Okay, so in this case, if you differentiate partially with respect to x, differentiate partially with respect to x. Okay, so let us suppose if you differentiate this partially with respect to x, then what comes out here is, look, first of all, differentiation of any function is f dash of z into inner differentiation dou z by dou x is equal to dou phi by dou x plus I times of dou psi by dou x. This is what you have here. Now try to understand something. We know that z is equal to x plus iy. Now if you differentiate this with respect to x partially, then what comes out? Dou by dou x of x plus I into dou y by dou x. Correct? This is what you have. So tell me one thing. This value is 1 anyhow, known to you. Whenever you are differentiating y partially with respect to x, what is the value? What is this value actually? What is the value of dou y by dou x? There is a variable y and you are differentiating that partially with respect to x. So what is the change in y when change in x direction is considered? Dou y by dou x. It's not dy by dx. Okay, it is dou y by dou x. So partial derivative of y with respect to x. When you are differentiating with respect to a particular variable, then all other variables are treated as constants. Correct? So if y is treated as a constant, dou y by dou x is how much? What is the value of dou y by dou x? 0, obviously. Correct? So this value is 0. So this implies your dou z by dou x is equal to 1 actually here. Okay, so dou z by dou x is 1, because obviously when you are differentiating partially with respect to x, you treat all of the variables as constants. Okay, so when you are differentiating with respect to x, when y is constant, differentiation of y is 0. Okay, so that's why dou z by dou x is actually 1. So therefore if you replace this dou z by dou x with 1, then your equation gets converted to f dash of z is equal to dou phi by dou x. So what is dou phi by dou x? We have seen initially in our differential analysis, dou phi by dou x. You see here, dou phi by dou x is x component of velocity u. So dou phi by dou x is x component of velocity, which is u, plus I into dou phi by dou x. So what is dou phi by dou x here? We can see again, dou phi by dou x is equal to minus v, correct? So we have this is minus v actually here. So this is minus v. So this function is generally written as w of z sometimes. Okay, so w of z. So therefore this implies f dash of z is equal to u minus iv, which is w of z generally. Now tell me one thing practically here. If this function has to be analytic, then this differentiation should exist at all points, yes or no? The practical meaning of this is, whenever there is some flow that's happening, at any given point there is some velocity for the flow, yes or no? It can be zero also, but it's not like there is no flow at that point, and basically we cannot talk anything about velocity. If there is some velocity, we'll say yes, velocity is plus 2 meters per second, minus 2 meters per second, the flow is not moving, zero. But you cannot say I don't know what is the velocity of the flow, correct? The flow has certain velocity physically. So that's why whenever you differentiate this, you are getting velocities of this component. Okay, this real part and imaginary part are nothing but velocities. So this velocities will practically exist at any point. That's why there won't be any point in the flow where you don't know what is the velocity. It's nothing like velocity is not defined, something like that. Practically when there is flow, there is velocity at every point. That's why these terms should definitely exist, and that's the reason of writing analytic here, and this is the definition of analytic. Is this clear to all of you? Yes. Now, so this is one thing. Here I want to ask you one thing. So if you want velocity at any point, you know, velocity is equal to velocity of flow at any point is equal to magnitude of velocity vector, which is square root of u square plus v square. And if you take magnitude of this modulus of this complex number, you will again get square root of u square plus minus v whole square, which is u square plus y square. So this is magnitude of f dash of z actually. Okay, so that's how this f dash of z should exist at all points. Then you can calculate the magnitude of the complex number. It can has some velocity. Both can be zeros. This f dash of z can be zero. Look, there is difference between 0 and does not exist. 0 means okay, fine, there is some value and that value is 0, so fluid is stationary at that point. But does not exist means you don't know that what is the velocity. Okay, that cannot happen in a flow. Now here if you see, this is in case of this Cartesian coordinate. Now if you see, we have f dash of z is equal to u minus iv. Okay, so what is u actually? We have written u are cos theta minus u theta sin theta minus I times of u r sin theta plus u theta cos theta. Now if you write this carefully, we can get this as, if you take u r common, then we have cos theta minus I sin theta, correct? So cos theta minus I sin theta. Next, minus I times of u theta if you take common. So minus I times of u theta if you take common, cos theta. Then this is minus u sin theta actually here. Okay, if this is minus u sin theta, that can be written as minus I sin theta again, because you see I into I gives you I square, which is minus 1. So this minus sign again gets compensated if you multiply. So if you multiply this term with this term, minus into minus plus I into I square minus, so there is one minus sign, u theta and sin theta. Okay, so if you write this, then this expression can be written as u r, this cos theta minus I sin theta is common in both the terms, so this can be written as u r minus I times of u theta into e power minus I theta. So this is one very important thing again in vertex flows which we will use. Okay, so f dash of theta is equal to, therefore f dash of theta in case of this complex functions is u minus iv, which is same as in polar coordinates ur minus I times of u theta into e power minus I theta, correct? So this is what you have. So this is the expression for the differentiation of this function f dash of z. Clear? So please type in the chat box, is this clear to you? Okay, now I want to ask you one thing. Have you known of this Milne-Thomson method? That's the last mathematical background that you need for solving this potential flows. Okay, so have you ever heard about this Milne-Thomson method? Milne-Thomson method, have you ever heard of this? No? Okay, fine, no issue. Okay, no issue, I'll teach you. So see here, what is this Milne-Thomson method is, look, for example, I'll directly solve an example, then you will easily understand that. Okay, so let f of z is equal to u plus iv, for example. Okay, or maybe anything, whatever you say. Okay, u plus iv, for example, if you see u plus iv, f of z is equal to u plus iv, then is analytic function and u is equal to, for example, x square minus y square. Okay, so let us say, for example, x square minus y square is analytic function and u is equal to x square plus y square. Then v is equal to dash. So what is the real value of v? For example, let us suppose they have given you one question like this. Now what you do to calculate this v is, look here, first of all it is given f of z is equal to u plus iv, correct? So what we'll do is we'll differentiate this partially with respect to x. So if you differentiate this, dou u by dou x plus I times of dou v by dou x. Now whenever this is dou v by dou x, if this f of z is analytic function, whenever f of z is analytic function u plus iv, this u and v, whenever this is analytic function u and v satisfy CR equations. They satisfy the CR equations. Okay, so u and v, capital V, I mean u and v, basically these two components here, they actually satisfy the 𝐂𝐤𝐬𝐿 equations. Okay, so when they satisfy the 𝐂𝐤𝐬𝐿 equations, you know, dou u by dou x equal to dou v by dou y, and dou u by dou y, the rate of change of u in y direction, is equal to minus dou v by dou x, correct? So only u is given to you, v is not given to you, but since you know that if the function is analytic, it satisfies the 𝐂𝐤𝐬𝐿 equations, this dou v by dou x can be replaced with minus dou u by dou y. For example, if v is given and they are asking you u, then in that case, since you don't know this quantity, you will replace dou u by dou x with dou v by dou y, such that you will make sure these two quantities can be calculated. Okay, so that's how you do this. So this implies f dash of z is equal to dou u by dou x, x square minus y square. So partial differentiation of that quantity is 2x plus I times of dou v by dou x can be written as minus dou u by dou y. So if you differentiate this, we'll get minus 2y is what you have. Okay, so this is what you will get. Now once you get this, we make one transformation here, that replace x by z and y by 0. Okay, so replace x by z and y by 0. So once you do this transformation, then what you actually get here is f dash of z is equal to 2 times of z plus I into 0, correct? So we have 0 here. Now what we do is f dash of z dz, if you multiply dz on both sides, 2z dz, and you can integrate. So if you integrate this, integration of f dash of z, which is f of z, is equal to integration of 2z, 2 is constant, integration of z is z square by 2, so we have z square plus some constant. Okay, so we have constant. So let us suppose here constant value is not given, so let us take the constant 0 directly. Okay, so this implies your f of z is equal to z square, z is nothing but x plus iy whole square. So this gives you x square plus I square y square, which is minus y square plus 2i into 2xy. So this is equal to x square minus y square plus I times of 2xy is what we have here. Okay, so once you see this f of z is u plus iv is what we have taken, so this value is nothing but f of z, which is your u plus iv, and if you check carefully, this u which is given in the question is same thing. This gets repeated here. Okay, so this method is one of the best methods to calculate the counterpart or the complementary function. Basically for this means if u is given, you can calculate v, the conjugate function, or if v is given, you can calculate u. Now why I have told you this is, whenever you take this f of z as potential function plus I times of stream function. Now did you understand? If potential function is given, how to calculate stream function? If stream function is given, how to calculate the potential functions? Clear? Yes or no? So please type in the chat box. Clear? So this method, what I have done now, is called Milne-Thomson method, and this transformation of replacing x by z and y by 0. Of course, this is a very small example, so you may not appreciate the beauty of this, but whenever we go for this vertex flow source and sink concepts, this method is one very powerful method that it normally if you do by doing the integration of the stream function, all these things, you will get some large solution, but this solution will be obtained in hardly some 4 to 5 lines. Okay, means if velocity potential function is given, you can calculate stream function in just 2 to 3 lines or 3 to 4 lines maximum. That's it. Okay, okay, so will you try one question? Will you try one question? Okay, so please type in the chat box, will you try one question? Shall we try? Actually, normally you might have seen these questions when phi is given, calculation of psi in some different methods, like they will do dou phi by dou x, then they'll calculate u, then they'll equate this to dou psi by dou y, then integrate them with respect to y, calculate the constant, then substitute again in dou phi by dou y. They'll do all these things, but this method is one very simple method. Actually, I'll show you how come. If for a 2D flow, let us suppose for a 2D flow, if phi of x comma y is given by log root of x square plus y square to the base e, then psi of x comma y is dash. Now practically, if you want to integrate this logarithms and all, you will takes so much of time, right? Now let us try to solve this question using the technique what we have discussed in the Milne-Thomson method. Okay, so first of all, f dash of z or f of z is equal to u plus iv, or generally phi plus I times of psi. Okay, so this implies f dash of z is equal to dou phi by dou x. So what is dou phi by dou x? Integration of this quantity. So normally if you see, we can write this. Okay, let us write 1 by root of x square plus y square into, because log of differentiation is 1 by this quantity whatever is there, differentiation of square root of 1 x square plus y square is 1 by 2 root of x square plus y square into derivative of this with respect to x, is 2x. So dou phi by dou x plus I times of dou psi by dou x is there. So dou psi by dou x is nothing but minus dou phi by dou y. So minus dou phi by dou y. If you differentiate this with respect to y, 1 by root of x square plus y square into 1 by 2 root of x square plus y square into 2y is what you have here. Okay, so this is the term. So this is f dash of z. Now using Milne-Thomson method, if you replace x with z and y with 0, replace x with z and y with 0. So whenever you replace y with 0, this y is 0, so this total term is 0. Imaginary term goes to 0. Whenever y equal to 0, this term is 0, this term is also 0. So what you have, square root of x square is x, square root of x square is also x. Okay, so 2 gets cancelled. This x can cancel 1 x square here. Then we'll have only 1 by root of x square in this case. Means basically you have f dash of z is equal to 1 by root of z square is what only left. So this is 1 by z. So if you integrate this, integral f dash of z dz is equal to integration of 1 by z dz, which is ln z. So if you expand this, you know, ln root of x square plus y square plus I times of tan inverse y by x is what you have here. So this is the stream function here. That's it. So this is the stream function which is given here. But definitely this expression is very good. But whenever you substitute this transformation, see, this complete term becomes 0, and in this term also only some small quantity is left. Majority got eliminated. Okay, so but normally if you want to calculate the same solution using the conventional methods, what you see in books generally, they will first calculate u is equal to dou phi by dou x. Then whatever the value you get, they'll write it equal to dou psi by dou y. Then they'll write psi is equal to integration of u into dy. All these things, and finally again one more substitution. This is what you see a lengthy procedure in books, but normally this complex calculus can greatly reduce the size of the solution. Clear? Understood? So did you understand how, if phi is given, how to calculate psi? Or generally if psi is given, then what you will do, you will write this expression as dou psi by dou y. That's it. Clear? Fine. This is one very powerful technique for solving this counterparts. Means if stream is given, calculating potential function, or if potential is given, calculating stream function. So these are the basics of some. So why you are replacing the terms like that? Because normally I'm not doing the transformations. You have to go to something called Jacobians to show that. Okay, right now I'm not doing the mathematical analysis. I'm just giving you the method. Maybe in complex numbers when I'm teaching, I'll show you that. Okay. Normally normally when we are teaching in maths class also, we don't explain the reason behind it. Okay, because the reason for replacing is Jacobians, what we called. If you, I don't know, you might have told that this there will be terms like this: u comma v, x comma y, this kind of things, because of which you will actually do this replacements. Okay, so I'm not giving you the details of that. We will see that in details in a maths course. Okay, that too in a comprehensive course we'll see. Some basic flows. Okay, fine. So let us see what is this, some basic flows. For example, so normally if you take a uniform flow, can happen in x direction, in y direction, or it can happen at some inclination to theta, inclination to x axis. Anything can happen. So let us see in a step by step way. You will understand this. Okay, so let us see here. Origin x, y. Okay, now try to understand this. Let us suppose you have the flow in this direction. For example, the flow is in this direction. So there is some flow in this direction, in the x direction basically, at some velocity, free stream velocity. Since there is no viscosity, all the layers moves with uniform velocity, and equal velocity, of course. Okay, so let us suppose there is some flow acting in this direction. There is some flow in the x direction at a velocity of capital U. Now, how you write the complex potential function for this? Because for any flow, if you know how to write the complex potential function, that's it, it's finished. Okay, so see here, how with the mathematical background that we discussed so far. So let us see here. First, for example, uniform flow along x direction. Uniform flow along x direction. Okay, now, so see carefully here. I want to give you some hint that directly I am going to give you the function f of z is equal to capital U times z is the complex potential function here. Okay, how do I know that that's the complex potential function? Very easy. See, we have f dash of z is equal to u minus iv. Correct? You know this, where u is the x component of velocity, v is the y component of velocity, we have seen. So for this flow, please type in the chat box what is the x component of velocity. This is a uniform flow along x direction. So what could be the x component of velocity in this case? There is some flow in the x direction, correct? So what is the x component of velocity in this case? U, capital U, correct? What is there? So this capital U is capital U itself. Okay, so capital U is capital U. Good. Now what about v? The flow is taking place in the x direction. So what is the y component of velocity in this case? Is there any y component velocity for these particles? No, correct? All the particles are translating in the x direction, so there is no y component of velocity. So v is 0. So this implies f dash of z is equal to u. So this implies f of z is equal to uz. That's it. Okay, means normally if you multiply dz, okay, let me write that step also because some of you may feel difficulty. So is equal to capital U. So let us say dz and integration. So if you integrate this f of z is equal to u is constant into integration of dz is z, plus constant is also there. That constant is arbitrary, so we drop that constant by taking that constant value 0. Okay, so this is how we get the complex potential function in case of uniform flow, okay, in x direction. Now if you see, this uz is equal to u into z is nothing but x plus iy. So this function f of z is given by u times of x plus I times of uy. So here we know, since this function f of z is equal to velocity potential plus I times of stream function, then this value ux is potential function and this is stream function. So if you want equipotential lines and streamlines, you know phi of x comma y equal to constant. So for equipotential lines, what you have, this phi is equal to constant, correct? Means u into x is equal to constant. So this implies x is equal to some constant divided by u. So x is equal to constant. Okay, so x is equal to constant. So please type in the chat box x is equal to constant are nothing but the lines in the vertical direction. Yes or no? Means if you take these lines, the lines, all these lines have x is equal to constant actually. Okay, of course in the negative direction also if you want you can take, but I'm just plotting in the first quadrant. The situation is same in any quadrant. Okay, so here if you see, all these lines are equipotential lines, means they have the same potential function value. Yes or no? Correct. So if you see, all these lines are equipotential lines. So phi of x comma y is equal to constant here in this case. Phi is equal to c1, phi is equal to c2 and so on. Maybe phi is equal to some cn here in this case. Then coming to the streamlines. First streamlines, this stream function has to be constant, which means this uy should be constant. Uy is equal to constant. So y is equal to some constant by u, which gives you again some other function c2 for example. So y equal to constant are nothing but this horizontal lines along the flow direction. Yes or no? Correct. So these are these are the stream lines here. Okay, so psi equal to C1, psi equal to C2, psi equal to C3, and so on. Psi is equal to Cn is what you have here. Okay, so this is psi is equal to Cn is what you have here. Now if you see, we already know the fact that equipotential lines and stream lines are perpendicular to each other, which you can easily see. Horizontal lines are the stream lines and vertical lines are the equipotential lines. They are perpendicular to each other. Okay, so this angle at every point of intersection is 90. Okay, and practically speaking, there cannot be any flow across the stream lines, so there is no y direction component for the flow. So all these are the stream lines and the equipotential lines. Clear? So did you understand with the help of this simple example? Basic flows actually. Okay, some flow along the x direction. Clear? Okay, so did you understand how? Because initially I know that it is UZ, I have written UZ, but this is how you actually derive this f of z. Okay, now let us see the case uniform flow along y direction. Uniform flow along y direction. Guys, I forgot to tell you one thing. In Milne-Thomson method, let us suppose if you are dealing in polar coordinates, for example, okay, then replace r with z and theta with 0. Okay, so that's what you have to do in case of Milne-Thomson method. Let us make a statement there, otherwise you will forget. So what happens in polar coordinates? Okay, let us write here. In case of polar coordinates, replace r with z and theta by 0. Okay, so like x with z and y with 0, similarly here the first variable with z and theta with 0 is what you will get. Okay, so this is how you do the analysis. Fine, so this is what you have. So in case of polar coordinates, replace r with z and theta by 0. Clear? Now, so this is what you have. And so now uniform flow along y direction. So let us see. X and y. So let us suppose the flow is along y direction, vertically upward direction, for example. There is some flow which is taking place in this direction. Okay, so these are the directions. So let us suppose if this is having some velocity u, in this case capital U, for example. Okay, so there is some uniform velocity, uniform flow with this particular velocity. Then in this case we know u and v. So please tell me what are the components of this. What is x component of velocity in the flow? So type in the chat box what is x component of velocity in this flow. Flow is happening in the vertically upward direction. So whenever flow is vertically in the upward direction, what is x component of velocity? 0, right? So u value is 0. What about v? Capital U, correct? So uv is capital U, the free stream velocity in this case. Okay, so therefore f dash of z is equal to u minus iv is what you have. U minus iv, which is minus I times of u, is what you have. Okay, so this implies f dash of z dz is equal to minus I times of u dz. So if you integrate this, we'll get f of z is equal to minus I times of uz is what you have here. Okay, so this is the function basically. Yeah, y is u basically, correct. So now if you replace z is equal to x plus iy, because z is complex number, so minus iu times of x plus iy, then we get this expansion as minus I times of ux, or minus ux times I, plus minus I into I square. So minus of I square is plus 1. So this is uy. So we have the equation uy plus I into minus ux is what you have here. Okay. So this is the complex function in real part plus I times of imaginary part. So this is the potential function phi of x comma y, and this minus ux is stream function psi of x comma y here. Okay, so this is stream function. Now if you see equipotential lines and stream lines again, for equipotential lines the story is same. For equipotential lines, what you have, phi is of x comma y is equal to constant. So this implies, since u is actually constant, y is equal to constant. Okay, so these are the equipotential lines, y is equal to constant. For stream lines, psi of x comma y is equal to constant, and this implies, what is psi here, minus ux is equal to constant. So minus sign if you delete in the arbitrary constant, because this c I can take negative also, so x is equal to constant is what you have generally. So this is x is equal to constant are the stream lines. Okay, so x is equal to constant is nothing but the lines which are parallel to y axis. So these are the stream lines, and there cannot be any flow across the stream lines. Flow is happening in this direction. Okay, and obviously equipotential lines are perpendicular to this. So if you draw, so we have this case like psi is equal to c1, psi is equal to c2, and so on. Basically psi is equal to some cn. Okay, similarly phi is equal to some c1, phi is equal to c2, and so on. Phi is equal to some cnn, and these are again orthogonal to each other. Okay, okay, so these are orthogonal to each other at all these points. Clear? So that's how in this case streamlines are in the flow direction. Obviously streamlines will always be in the flow direction, and this equipotential lines are perpendicular. Okay, from the simple analysis. Clear? Yes or no? Are you all feeling things easy for writing the velocity potential function? This arbitrary constant, we are taking it to be 0 and directly dropping it to 0. That's it. Okay. Flow inclined at an angle alpha to x axis. Flow inclined at an angle alpha to x axis. Okay, so flow inclined at an angle alpha to x axis. Clear? So let us see this. Okay, so origin x, y. Now let us suppose you have the flow which is inclined to x axis at some angle. There is some flow like this which is inclined to x axis. Okay, like this. Now if you see, look, if you take any, and this flow is actually inclined at some angle alpha to x axis. Now if you take any particle in the flow, for example, let us suppose if this is moving at some phase stream velocity u, for example. Okay, so the phase stream velocity of the flow is u. Then in this case, if you resolve x component of velocity and y component of velocity, this is alpha because the angle made with horizontal is alpha. So in this case, please tell me what is x component of velocity and y component of velocity. So type in the chat box what is x component of velocity. So please type in the chat box in this case what is x component of velocity here. What is x component of velocity in this particular case? U cos alpha, correct? U cos alpha, right? So U cos alpha. And what about y component of velocity in this flow? Yeah, U cos alpha, correct? And V is basically U sin alpha, correct? Both are in the positive direction, so we'll take plus. So now if you see, therefore f dash of z is equal to, which is u minus iv, so u cos alpha minus I times of u sin alpha. Okay, so this gives you f dash of z is equal to u times of cos alpha minus I times of sin alpha minus I times of sin alpha. Okay, now alpha is actually some constant value and u is also some constant value, correct? Yes, u sin alpha. So now if you see this cos u is actually some constant value, it's moving at some uniform velocity. This is a uniform flow and this alpha is also constant. Okay, so this cos alpha minus I sin alpha can be written as u into e power minus I alpha, correct? That can be written as e power minus I alpha. Alpha is also some constant because cos alpha minus I sin alpha can be written as e power minus I alpha. So on integrating, so this implies f dash of z dz is equal to u into e power minus I alpha times dz. You multiply dz on both sides and if you integrate this, this gives you f of z is equal to u is constant, e power minus I alpha is constant into, so integration of dz is z, that's it. Okay, so if you expand this, u e power minus I alpha into z is x plus iy is what you have here. Okay, so x plus iy is what you have. So this implies your f of z is basically given by this function. Okay, so f of z is equal to u e power minus I alpha into x plus I into u e power minus I alpha times y. Okay, so this is what you have. So this is equipotential function and this is stream function in this case. So this is phi of x comma y and this guy here is psi of x comma y actually here. Okay, now try to understand one thing. So if you see u e power minus I alpha into y is actually constant. Let us suppose, for example, you know, these are the streamlines of the flow. So first streamlines, psi of x comma y is equal to constant. Psi of x comma y is equal to constant actually here, correct? So whenever you see this, look here, this is actually the wrong thing that we have written here because we have to slightly expand it. I will show you how to expand. So see here, u into e power minus I alpha cos alpha minus I sin alpha into x plus iy is what you have to split and then you have to multiply both the complex numbers, then you can get the real part and imaginary part. Okay, so let us split that. So if you split this complex numbers, x into cos alpha plus y into sin alpha is what you will get the real part, correct? U times of cos alpha into x minus I into plus I is minus I square, so that is plus 1. X cos alpha plus y sin alpha, x cos alpha plus y sin alpha, so this is the real part, plus I times of imaginary part is y, y cos alpha minus x sin alpha, y cos alpha minus x sin alpha. So this is what you have actually here. Okay, so this is the complete complex function. So here in this case, the function, if you write, therefore f of z is equal to u times x cos alpha plus y sin alpha plus y sin alpha plus I times of u into plus I times of capital U into this capital U is in common multiplication, y cos alpha minus x sin alpha. Okay, just you have to do simplifications little carefully, minus x sin alpha. Okay, so now if you see, this part which is here is the velocity potential function, and the part which is here is the stream function. Okay, now try to understand something. Look, first streamlines, psi of x comma y is equal to constant. That you know this. So psi of x comma y equal to constant. So this implies u times of y cos alpha minus x sin alpha equal to some constant. So u is actually some constant value. So if you divide this capital U here, we will get the equation as minus sin alpha into x plus cos alpha into y is equal to some constant. C by capital U is c dash, for example, let us say. Now if you see this equation, this equation is of the form of a straight line, yes or no? This equation is of the form ax plus by plus c is equal to 0, correct? Yes or no? A some constant, alpha is actually some constant value, the flow is inclined at some fixed angle alpha, so this sin alpha is constant, so minus x sin alpha is constant value, and cos alpha is also some constant, so is equal to c dash. So let us suppose if you write minus c dash, that can be written as plus c dash. Anyhow, whatever you want conversion you can take. You can write minus c dash or plus c double dash, for example, some other variable is equal to 0. Can you write this equation? So when you write this equation is of this straight line equation. So obviously one thing is very clear, streamlines are straight lines. Okay, now how are these straight lines? If you calculate slope of this equation, can you please tell me what is the slope of this equation? What is the slope of this equation? It's a straight line equation, so what is the slope of this equation? Minus a by b, which is correct. 4. Flows in a sector. Okay, we'll I think we cannot complete this today, only 10 minutes is left, but I'll give a start to this. Okay, so let us suppose you have this complex function f of z is equal to some u times of, so let us suppose there is some velocity u times of z to the power n. Okay, so let us suppose you have z to the power n, for example. Okay, we'll see how this is actually some flow in a sector, all these things. So now if you see, f of z is equal to capital U times of z power n. Now if you see, so if you differentiate this, we'll get, so this can be written as u times of r into e power I theta whole power n actually. Okay, so this is u times r power n into e power I times of n theta is what you have, correct? I theta whole power n can be written as e power n theta. Now if you differentiate this, because you want f dash of z, this implies f dash of z is equal to, if you differentiate with respect to small r in this case, then we have u times of if you differentiate with respect to small r actually, then we have, okay, we can have actually here, so in this case if you differentiate with respect to small r, n into r power n minus 1 into e power I n theta is what you have here. Okay, so this if you split into real part and imaginary part, then you can write this as f dash of z is equal to then u n r power n minus 1 into this cos n theta plus I times of sin n theta is what you have. Okay, so this expression gives you if you make one small adjustment here, look, before writing this term, because I want to show you one particular result, so here this e power I n theta, I can write this as e power I n plus 1 times of theta into e power minus I theta, correct? I can write this because I have added plus 1 I theta and I am subtracting 1 minus I theta. So this, if you expand, you have u n r power n minus 1 into this cos n plus 1 theta plus I times of sin n plus 1 theta into e power minus I theta is what you have here. Okay, so this is what you have. So this is equal to if you write carefully, u n into r power n minus 1 cos n plus 1 theta, cos n plus 1 theta actually here, so cos n plus 1 theta, and this can be written as minus I times of minus u n r power n into r power n minus 1 actually into sin n plus 1 theta, this total value multiplied with e power minus I theta, because this is in polar coordinates is what we are writing, right? So how are we writing n as subscript of u? This is not subscript, this is multiplication. Okay, I think you are feeling this as subscript, but this is actually multiplication. Okay, u into n. Okay, I think it's fine now. Maybe here also you may feel the same thing. It is not subscript. Okay, multiplication. Fine. Okay, Shrikant, this is not multiplication. Okay, now we can see this f dash of z in polar coordinates. We have observed this f dash of z is equal to u r minus I times of u theta into e power minus I theta, correct? So this is what we have seen. So therefore, if you compare the radial velocity and this theta velocity, okay, so if you see this radial velocity and theta velocity, we can see u r in this case is equal to, therefore u r in this case, the radial velocity in this case is equal to u into n r power n plus 1 into n minus 1. Okay, so r power n minus 1 into this cos n plus 1 theta, cos n plus 1 theta, and u theta in this case is minus u n r power n minus 1 into sin n plus 1 theta is what you have here. Okay, so these are the radial and theta components. Now if you put n is equal to 1, for example, for n is equal to 1, let us see what happens when you put n is equal to 1. You have differentiated this partially with respect to r actually. So whenever you differentiate this partially with respect to r, look, f of z, if you differentiate this partially with respect to r, just a minute, f z is equal to dou by dou r of this quantity f dash of z into dou z by dou r. So dou z by dou r gives you e power I theta. Okay, fine. So I think there is some, yes, that's what I'm thinking, small, there is some small mistake here. Okay, so see here, whenever you differentiate this partially with respect to small r, you will get one more thing. What is that? These terms, if you have written, so please strike off these things, because we made one small mistake here, because we missed one small r here. Okay, look, I want to show you something. See here, whenever you differentiate this partially with respect to r, you have f dash of z into dou z by dou r. So what is dou z by dou r? Z is equal to r into e power I theta, correct? So this implies dou z by dou r gives you e power I theta. Okay, yeah, so this is what you have. We missed this term. So dou z by dou r into e power I theta. Okay, so then u into n into r power n minus 1 into e power I n theta. So this can be written as f dash of z into e power I theta is equal to u n r power n minus 1 into cos n theta plus I sine n theta. Yes, it should be n theta, correct. N theta. So this can be written as cos n theta minus I times of minus sine n theta is what you have. Okay. So if you multiply this, u n r power n minus 1 cos n theta minus I times of minus u n r power n minus 1 into sine n theta. Okay, so this is what you have. Now if you see carefully, f dash of z, so this all thing what you have is e power I theta, but if you write f dash of z, this gives you u n r power n minus 1 into cos n theta minus I times of minus u n r power n minus 1 sine n theta, this total value into this e power I theta here on the left hand side. If you shift this to the right hand side, we get e power minus I theta, correct. So we get e power minus I theta here. Now if you see, we have the general expression f dash of z, in this case is u r minus I times of u theta into e power minus I theta, correct. So if you now compare this equation with that particular equation, then we know u r radial velocity is equal to this quantity which is here, u n r power n minus 1 into cos n theta, okay, and u theta is equal to minus u n r power n minus 1 sine n theta, correct. So we have this particular expression. Okay, now for n is equal to 1, if you keep n is equal to 1 in this case, for n equal to 2, 3 we have different values. So first of all, for n is equal to 1, if you replace for n is equal to 1, for n is equal to 1, this f of z gives you uz, correct. This uz is nothing but the flow, this uz is nothing but the potential function for the flow, uniform flow in the x direction. Let us see what we'll get here. This radial component ur is equal to, and u theta, let us see what are these values. So ur and u theta is equal to, when n is equal to 1, this 1 minus 1 goes to 0, correct. So r power 0 is 1, this n is also 1, and this n is also 1. So u cos theta is what you have. So u cos theta, and similarly here this is 1 and this is also 1 and this is also 1. So total minus u sin theta, minus u sin theta. So this is the radial and the theta components. Okay, so from this, if you want to calculate, you know, this cos theta can be actually written as x by r, and this sin theta can be written as y by r actually here. Okay, so instead of that, if you try to convert this to Cartesian coordinates, therefore u is equal to ur cos theta, so u square, I mean u cos square theta minus u theta into sin theta. So minus of u theta into sin theta gives you plus u times of sin square theta. So this is equal to u. Similarly, v is equal to ur sin theta, so u cos theta into sin theta plus u theta into sin theta, sorry, u theta into cos theta, correct. So let us see, u theta into cos theta, it should be u theta into cos theta, right. So u theta into cos theta, fine. So if you do u theta into cos theta, u theta is minus u sin theta into cos theta. Okay, so now if you simplify this result, then this term and this term both gets cancelled and v is equal to 0. So that's how you have x component of velocity as u and y component of velocity as 0 from this particular equation. Okay, so therefore this flow for n is equal to 1, the flow is a uniform flow along x direction. A uniform flow along x direction. Okay, so that's how, basically, because when you put n equal to 1, you know, this becomes uz. So whenever it is uz, all these equations mathematically whatever you're getting, that equation should again represent the same equations as that of uniform flow in the x direction. Clear? Okay, so please type in the chat box here, this e power I theta should be there because of this expression. Initially we missed that, but this is the correct expression. Okay, Did you understand how I have written u and v based on this ur and u theta available? Small u is equal to ur cos theta minus u theta sin theta. So that's what I have done here. Similarly, v is equal to ur sin theta plus u theta cos theta. So if you do that, we'll get 0 here. That's it. Okay. Fine. Okay. So is that clear? So all of you. So please type in the chat box. Is this clear to all of you? Okay. So we'll see for the case of n equal to 2, n equal to 3 maybe in tomorrow's session, because I think time is short. We have only 1-2 minutes left. So we will stop the session here for now. But before closing, I would like to show you what we have done today. So yeah. So we have seen what is potential flow, and then we have talked about some basic funda that we have covered in this differential analysis of fluid systems. Then in this case we have talked about the stream function and the velocity potential functions. This is how we got them, and then we discussed some basics of the complex numbers, and also we have seen the conversion of Cartesian components of velocity to the polar coordinates as per this matrix system actually. So we have seen this analysis. Okay, u and v analysis. Then we have seen the complex potential function. I have defined what is analytic function, and we have seen the way it should be analytic, because this u and v should always exist. Okay, so at any point if you calculate magnitude of f of z, you will get the result. Okay, then we have converted this f of z in terms of scalar and also in terms of polar coordinates. Okay, so then Milne-Thomson method I have discussed. Then some basic flows. Okay, flow along x direction, this is along y direction. Okay, this is inclined at some angle. So and finally this is some generalized case, flow inside some sectors. Okay, so this is how we got the case. Clear? Okay, so if that's clear, then we will close this session for now, and we'll meet tomorrow. In tomorrow's session we will talk about the vertex flows, concept of circulation. Okay, and this n equal to 2, n equal to 3, we'll see some 2-3 more cases here, and we'll talk about source and sink concepts in the first lecture. Okay, so that lecture is very much important, so don't miss the session. Clear? And in the next session we'll start talking about the superposition of flows. Okay, like basically these cases of flow past a cylinder, flow past rotating cylinders, all these things it turns out. Okay, easy. Potential flows, did you all understand based on the complex numbers and simple multiplication of complex numbers how we are writing all these things? The only thing is you should do basic math little carefully, no complicated maths. Okay, multiplication of complex numbers, this multiplication of I into I, these things you have to do little carefully. That's it. If you can do them, that's it. Everything is very simple. Fine. Okay, so then thank you all. We'll meet again at tomorrow 7 PM and we will discuss the things. Okay, fine then. Thank you all. Thank you. Okay, we'll meet again at 7 PM tomorrow and we'll discuss. Thank you a lot. Yeah, good night all of you. Take care. We'll meet tomorrow. Thank you.